So, now let us look at heterogeneous nucleation. Heterogeneous nucleation, as we have already discussed, refers to the nucleation starting on a pre-existing surface and interfaces. There will already be some pre-existing surfaces, and there the nucleation happens much easily. So, here we are looking at a nucleation on the case of a flat surface. So, when you have a liquid pool and you are having a solid nucleus on a flat surface here, then we can actually see three different interfaces: the interface between solid and liquid, interface between the surface on which the interface between the liquid and the surface on which the solidification is happening, the green line, and the interface between the solid and the surface on which solidification is happening, the blue line. So, each of these surfaces have certain surface energy. So, this is what we call gamma SL, the surface energy between solid and liquid interface, and gamma IL is the I refers to the interface of the solid on which the solidification is happening. So, gamma IL refers to the surface energy between liquid phase and the surface on which the solidification is taking place, and gamma SI indicates the surface energy of the interface between the solid and the solid nucleus and the solid surface on which nucleation is taking place, right. So, now let us look at the force balance here. So, the surface tension force in the plane of the surface is given by gamma IL equal to gamma SL cos theta plus gamma SI, right. This is something that one can use in order to write your expressions for delta G or in general. However, we are not going through that derivation of how one would obtain the delta G star for heterogeneous nucleation. So, if you are interested, I encourage you to go through the textbook of Reed Hill on physical metallurgy. There you have a derivation, you have the derivation for for finding the delta G star for heterogeneous nucleation, and you will see that the heterogeneous nucleation's activation energy for heterogeneous nucleation is related to activation energy for homogeneous nucleation times some function of theta, right. So, this theta is what we call wetting angle, as we have shown in this figure, right. So, f of theta is given by this formula for a spherical particle, and you can see that the value will always be less than 1. Okay. So, you can see that delta G star heterogeneous. So, for the free activation energy for heterogeneous nucleation is always going to be less than the activation energy required for homogeneous nucleation. However, the R star remains the same. So, this is gamma between solid and liquid interface. So, the solid and liquid interface, solid means our nucleus, solid nucleus and liquid interface, gamma is going to be same whether you are having homogeneous or heterogeneous, the surface energy surface is going to be the same, and hence the R star value is not going to change. Okay. So, for homogeneous and heterogeneous nucleation, for the same critical radius, you see that you need much lower activation free energy for heterogeneous nucleation compared to homogeneous nucleation. That is why it is much easier to have heterogeneous nucleation. So, heterogeneous nucleation happens much more readily than homogeneous nucleation. All right. And if you see the degree of undercooling required for heterogeneous nucleation and homogeneous nucleation, this graph clearly shows that the n dot for homogeneous nucleation curve is little down from heterogeneous nucleation. So, this is what we have looked at the red curve before. The heterogeneous nucleation turns out that the degree of undercooling required for heterogeneous nucleation is only few degrees Celsius, not few hundred degrees Celsius like homogeneous nucleation. That means the heterogeneous nucleation can actually happen at much higher temperature than homogeneous nucleation, right. And as a result, the curve shifts upwards, all right. So, the undercooling for heterogeneous nucleation is less than the homogeneous nucleation, and the maximum nucleation rate n dot for heterogeneous nucleation occurs at higher temperature than for homogeneous nucleation rate. All right. So, having looked at now having understood the concept of nucleation and the two different types of nucleation, homogeneous nucleation and heterogeneous nucleation, and the nucleation rate, that means rate at which the number of nuclei are forming in these two different types of nucleations. Now, once you have certain nuclei formed, and the next step is growth of this nuclei, right. That means more and more liquid has to come through diffusion and join the solid phase in order to increase the size of the solid phase. So, as we have discussed, the growth begins when embryo reaches a critical radius r star. So, below that radius it again dissolves, but only when the nuclei reaches this radius r star, only embryo reaches this radius r star, that is when it is called nucleus, and it is ready for growth. So, once you have a certain nucleus formed at one place in the liquid solution, while this is growing, there it is still possible that the nuclei can still continue to form at other locations, right. So, they can happen simultaneously. So, the nucleation continues elsewhere in the liquid phase, and however, this growth process ends. So, suppose if you have one nucleus here, another nucleus here, and then this guy is growing, this guy is growing, and then the moment these two guys hit, that means when these two nuclei which are growing, this growth process ends when the particles of new phase meet in any region. So, if you are here, then the growth here stops, and then it continues in this region, and so on. As we can see that the particle growth happens through long range atomic diffusion in different stages. So, what are these long range atomic diffusions? You can have the diffusion through the parent phase is the, for instance, liquid phase, and diffusion through the phase boundary from the liquid phase to the solid phase. Through the phase boundary, it has to cross the phase boundary, and within the solid phase again there has to be some diffusion. So, diffusion into the nucleus from there, right. So, the growth rate can be described like the rate of diffusion, which is pretty similar because the growth is a diffusion process. So, the growth rate can be described by a Arrhenius type of equation as shown here. G dot is equal to C times e power minus q by kT, where q is your activation energy, which is temperature independent, and C is our temperature independent constant, right. So, now if you would plot the growth rate G dot, it looks like this green curve. This is our growth rate. As you are at higher temperature, you know that the diffusion is faster at higher temperature, and as a result you will have higher growth rate. At low temperatures the growth rate is low, and this is the red curve is only a part of the nucleation rate. This is, there is also somewhere here, but we have not shown that. This is our nucleation rate. Okay. So, now you have certain nucleation rate and some growth rate, and now you can actually plot the overall transformation rate using these two quantities, and the overall transformation rate looks something like this. So, the overall transformation rate increases as you reduce the temperature and reaches a maximum value, and then it starts decreasing again, because at this point your although your nucleation rate is increasing, but your diffusion is decreasing significantly, and hence your overall transformation rate reduces. At the top we have very high nucleation rate and low nucleation rate. So, that means very few nuclei, number of stable nuclei will be less at high temperature, but the growth rate is large. That means the rate at which the particle grows is very large here. That means the diffusion can happen over long distances at high temperatures. So, the rate of transformation, that means the rate at which this transformation takes place, overall transformation rate, and of course, the time required for the completion of the transformation to certain degree should be inversely proportional, right, because if you are having a faster rate, then the time required for transformation will be less, right. So, here we are showing this is the rate of transformation as a function of temperature, that rate of transformation to say for instance 50% transformation rate. Then because these two are inversely proportional, you can see on the right hand side here this is the time required for transformation to finish 50% quantity. That means, if your transformation from liquid state to solid state is happening, if your 50% of liquid is converted to solid state, so what is the time required for such a thing at different temperatures? If you would do that, then you will get curve like that. That means, you will have a minimum temperature at certain temperatures, minimum time required for transformation to 50% at a certain temperature. Above that and below that, you need to spend more and more time. All right. So, now the size of the product phase particles depends on the transformation temperature. At which temperature are we doing transformation? If the transformation is taking place close to the Tm, meaning, so let us say if the transformation is taking place close to this value somewhere here, then that means you are having the transformation is happening at higher temperature. As a result, your nucleation rate is low, that means it has low nucleation rate and also number of stable nuclei are less, but very high diffusion rate. And hence, what we have is, we have few nuclei growing over large size to coarse grain microstructure, because you have very few nucleus, but all of them are growing over larger distances because of the higher diffusion rate, and hence your microstructure will be a coarse grain microstructure. But if the transformation is happening at a lower temperature, which corresponds to high nucleation rate, that means there are several nuclei, but low growth rate because the diffusion is very low. So, several nuclei are there, but their growth rate is small and hence they cannot increase their size significantly, and as a result you have a fine grained microstructure. So, the microstructure of the particles will be fine grained, and if the material is cooled rapidly, if you are cooling the material extremely fast in the transformation temperature range, so the situation basically corresponds to very low transformation rates, right. As you can see, the transformation rate first increases and then decreases. So, when it is cooling down rapidly, that means you are actually hitting very low transformation rates, and as a result you would be producing non-equilibrium phases, and that is what happens when you have non-equilibrium phase. We have seen how the microstructure changes, and we will see in detail how the microstructure is going to change. So, the kinetics of solid state transformation is something that we will discuss. So far we have looked from liquid state to solid state. Now, how the solid state transformation happens. Here again the kinetics discusses the time dependence of the rate of transformation, and usually the fraction of transformation or reaction occurred is described as function of time at a given temperature, right. That is how we describe this fraction of transformation. And how do we monitor the transformation? Usually the progress of transformation is monitored through microscopic examination or measuring a physical property such as conductivity, right. So, you measure the conductivity and then based on that you will be able to predict what fraction of the material has been transformed, and then the fraction of the transformed product is plotted against time on a logarithmic scale at a given temperature, right. So, now let us look at the fraction of transformation as a function of time. As you know that it takes some sufficiently long time depending upon the temperature at which you are actually doing this transformation. It takes some time for nucleation. So, initial time up to certain time there will not be any growth, because the system is nucleating particles or nuclei, and after nucleation is finished, that is when the growth begins, right. So, the fraction of the transformed product. So, on the y axis we are showing fraction of the transformed product. Here up to growth beginning there is no transformation, and as you are increasing the temperature from that stage, the fraction of the transformation increases asymptotically to 1, right. So, this state is our growth state. So, this equation, this curve looks like an S-shaped curve, which can be mathematically described by something called Avrami equation as given by this relation y equal to 1 minus e power minus k t power n, where t is the time, k and n are time independent constants which depend on temperature at which this transformation is taking place. So, here the rate of transformation is defined as the reciprocal of the time taken for 50% completion of the transformation represented by t.5. So, that means if you are talking about rate of transformation, you are saying that it is defined as the reciprocal of the time taken for 50% completion of the transformation. So, if you can see that here this is the time taken for 50% completion of the transformation, then the rate is described as 1 over T.5. All right. So, with that we have understood how a nucleation happens under different conditions, homogeneous and heterogeneous nucleation, and then we have discussed the concept of activation free energy and critical radius R star, and then how activation free energy changes as a function of temperature. Both R star and activation free energy change as a function of temperature, and we discussed that at low temperatures the activation free energy is low, and hence nucleation occurs readily at low temperatures compared to high temperatures. And then we have discussed the difference between heterogeneous nucleation and homogeneous nucleation, and we have looked at the fact that the heterogeneous nucleation has lower activation energy compared to homogeneous nucleation. Then we have discussed the concept of nucleation rate, and we have shown that the nucleation rate is going to have a maximum at a certain temperature, and the heterogeneous nucleation rate occurs at a higher temperature. Maximum value of heterogeneous nucleation rate occurs at a higher temperature compared to homogeneous nucleation, and the degree of undercooling required for heterogeneous nucleation is less than the degree of undercooling required for homogeneous nucleation. And then we have discussed the growth process and how the growth process is described by a diffusion like phenomena, and then we have shown that the growth is higher at high temperatures and reduces at low temperatures, because at low temperatures the diffusion is low, and the overall transformation rate also is shown to have a maximum at certain temperature below the Tm. And then we have also looked at the transformation rate as a function of time for different at different temperatures. And finally, we looked at the fraction of transformation as a function of time. So, as a function of time, how much amount of material has been transformed from parent phase to product phase, and that is described by Avrami equation, wherein the fraction of transformation when plotted against time looks like a S-shaped curve as shown here. Okay. In the next class, we will use this knowledge in order to understand the important concept called isothermal transformation, and we will diagrams in the particularly for steels. Thank you very much.